Okay, thanks, Lorenzo, and welcome everyone to the first session of this day. This is an invited talk by Anne Canteaut. And I guess Anne needs no introduction, but I've written something anyway, and I hope it's correct. So Anne's research in cryptanalysis contributed to the foundation of our understanding of the security of symmetric cryptography. The designs she contributed to enriched many cryptographic competitions. She served as program chair of our top conferences like FSE and Eurocrypt. She is an ISCR Curie Prize. And in addition to all of this, she supervised many excellent PhD students that contributed to our community, and some of them are present in this room. So please welcome Anne Canteaut.
So thanks a lot, Christoph, for the nice introduction, and thanks to you and Kazu and the entire program committee for this invitation. So when I received your invitation, I discussed with some colleagues around in order to select the best topic I could have for this talk. And so maybe I will try to summarize the conclusions of this discussion. So the conclusion is that there are two categories of people working in symmetric crypto. You have cryptographers with color photos and cryptographers with black and white photos. And the main difference between these two categories is that cryptographers with color photos, they do not have any knowledge of stream ciphers, while cryptographers with black and white photos were supposed to have some. And so this is the starting point of my talk. This is, well, how is it that those cryptographers with color photos, they extensively use stream ciphers, they need stream ciphers, but they don't know anything about them? And well, because I'm one of those black and white cryptographers, this question reminds me a talk given by Adi Shamir 20 years ago. So this was his invited talk at AsiaCrypt 2004, and it has this title, Stream Ciphers, Dead or Alive? And I believe that this question is still very relevant, or maybe I should say that it's very relevant again. So in this talk, I'm going to focus on this particular kind of stream ciphers, which are named additive synchronous stream ciphers. What does it mean? This means that the ciphertext is obtained just by adding the plain text to a key stream sequence, which is generated by from the secret key by a key stream generator. So, and as you can see, this the state of this keystream generator, it does not depend on the plain text, which means, for instance, that stream ciphers like ASCON or any cipher following the duplex mode does not belong to this category of stream cipher. So I choose to focus on this kind of stream ciphers first because I think that it's the most natural way we can find for having a practical version of the one-time pad. And also these ciphers were very nice because the keystream sequence can be computed offline, I mean, without knowing the plain text or without knowing the ciphertext when we, in the case of decryption. And so this means that the online phase is reduced to a minimum, just an addition. And also another argument in favor of this stream ciphers is the fact that they are agnostic of the length of the plain text. What I mean is, of course, in most protocols, the information is transmitted as blocks or as frames, but this is not in favor of block ciphers because the length of this block highly depends on the protocol that we are using. And so that's why stream ciphers may be more appropriate in this context. But despite all these arguments in favor of stream ciphers, what Adi Shamir explained in his talk 20 years ago is that the decline of stream ciphers was a very clear trend, and that it is unlikely to be reversed in the near future. And so why does it obtain this conclusion and observe this thing? Well, I would say that probably one of the main reasons of that is that there is a common belief in the community that stream ciphers are weaker than block ciphers. And well, actually, we have many arguments for this assertion. A first argument is that it appeared that many stream ciphers designed in the 90s appeared to be backdoored. And a second very strong argument, and you have to remember that this talk was in 2004, which was just at the end of a European project named NESSI. And this NESSI project, it aimed at recommending symmetric primitives, not only symmetric and asymmetric primitives, and all kinds of them. And what happened during this NESSI project is that the 6 submitted stream ciphers were broken, which implies that at the end of the project, the portfolio for symmetric ciphers was empty. So all those stream ciphers at that time appeared to be quite weak. And also, well, another reason is that one of the most widely deployed stream ciphers at the same time was RC4, and we identified statistical biases in RC4 which have been used for real-world attacks. So you can see that from this landscape, it's clear that it does not inspire high confidence in stream ciphers. And so, as I said, at the end of this NESSI project, we were not able to recommend any stream cipher. And so the community at that time wondered whether this was really a problem or whether it was okay and stream cipher could be abandoned. And what Adi Shamirs concludes in his talk is that well, stream ciphers are not that important, except in 2 very specific areas, 2 specific profiles for ciphers. The first one is hardware-oriented ciphers with a lightweight design. And the second type of area was software-oriented schemes with very high throughput. Well, it means similar kind of performance than as RC4. And so this is why a new project named eStream was launched at that time to find new stream ciphers, but having these 2 very particular profiles. So this eStream project, it was a part of a European project named eCrypt. And so it was a public competition, as we are used to, but for finding new stream ciphers for 2 different profiles. And so, as you can see, it defined a portfolio of 4 ciphers for software applications and 3 ciphers dedicated to lightweight hardware environments. And well, it's important to observe that the security requirements were not the same for the 2 categories. And in particular, for the software ciphers, the security requirement was 128-bit security, while for hardware cipher, it was only 80-bit security. And so this is why right after the end of this eStream project, we could see some variants of the hardware cipher that have been proposed in order to improve this security level and reach 128-bit security. So this is a case for Grain, for instance, and also for Trivium. So now we are almost, well, roughly 15 years after, more than 15 years after the end of this eStream project. And so what could we say about stream ciphers? Is that true that stream ciphers are still ciphers which are only used in these niche applications, or are they more widely used? Well, we can have a look at what happens for widely spread protocols. And so, for instance, well, you probably all know that in TLS 1.3, we are using 2 different ciphers, AES encounter mode which is a stream cipher, obviously, and Cha-Cha-20, which is a variant of Salsa, which was one of the winners of the eStream project. If we look now at 5G mobile phone communications, then we have 3 ciphers, which are all 3 stream ciphers. Again, AES in counter mode, but also SNOW 3G and Zook. And also we have seen new stream ciphers appearing during these last 15 years. So this is the case, for instance, of Shake, which is as a XOF standard included in the SHA-3 standard, which is based on Ketchak. And also we have a lot of new proposals of stream ciphers, which are dedicated to transciphering, which means that they aim to be combined with a fully homomorphic encryption. I will come back to this later. So it's clear from this picture that stream ciphers are not a niche area, that we have stream ciphers in many important protocols. And so what's the point? Why is it that stream ciphers look so important, but we don't really work on that? Well, my personal analysis of this is that because we don't have a lot of research on cryptanalyzing stream ciphers. So it seems that all these stream ciphers are not very attracting targets. And I guess that the reason of that is that it's probably much more difficult to define reduced version, weakened version of stream ciphers than for block ciphers. Because for block ciphers, it's quite trivial. We just reduce the number of rounds and have a weakened version, and you can try to attack it. For stream cipher, it's much more complicated. And so this means that probably we don't have very promising targets to be attacked. Well, that's at least my personal analysis. But if we come back to Adis Shamir's question, well, I would say that stream ciphers are alive because we have them everywhere. But I would say that stream cipher cryptanalysis is almost dead. And so the aim of my talk here is to try to motivate you to work on stream cipher cryptanalysis. Okay, so what I'm going to present in this talk is first, I will try to show you why stream ciphers provide a very flexible design, much more flexible than what we have in block ciphers. And then I will say some words about cryptanalysis, especially on distinguishers and on correlation attacks. And at the end, I will come back to this new context where stream ciphers are very promising candidates. So this is a case of transciphering. And I will say some words about the transistor, which is a new stream cipher proposal dedicated to this specific context. So let's see how a stream cipher looks like and why it is a quite flexible design. So a stream cipher, this is a finite state automaton, so it has an internal state. This internal state, it's denoted by xt here. And we have 3 different transformations in this design. So the first transformation, this is the initialization function, which takes as input the secret key and possibly a public initial value, and it outputs the initial state of the generator. And of course, there's a category of very important attacks, which are related IV attacks, which use some weaknesses of this initialization function, but I won't mention them here. I will always, my talk, I will suppose that the secret material, which is the main parameter of the stream cipher, is the initial state. And I will explain at the end why I will make this assumption. And so if we look at the key stream generator, then we have 2 different transformations. This function here, which is the next state function, so which computes the next internal state. And this function will be always denoted in blue. And we have the second building block, which is denoted in red, which is called the filtering function. So this is a function which extracts some bits from the internal state at each time instant and produce a corresponding keystream block, which is denoted by ZT at time t. And so we can see that the first obvious trade-off is between the size of the keystream block that is extracted at each time instant and the complexity of the two transformations, the next state function and the filtering function. And of course, if these two functions are very strong, then we can extract a large block of keystream. Well, if they are quite weak, then we will extract only, let's say, one bit or one byte. So this is the first trade-off. And a second trade-off is, of course, between the complexity of the next state function and of the filtering function. So if we look at one extremity of this trade-off, then we can choose a very simple next state function, so typically a linear transformation, which can be implemented by a linear feedback shift register. And what we need is that this function is a bijection, of course, and that the sequence formed by the successive internal state, it has a high period, which can be done with linear feedback shift register with primitive feedback polynomial. So in this category, we can find a very old design named nonlinear filter generator. So in that design, the filtering function is usually a function which takes as input only a few bits of the internal state, like typically 20 or 30 bits, and which outputs a single bit. But of course, we can use a much stronger filtering function and then output a larger keystream block at each iteration. And this is what we do, for instance, in the counter mode of operation. In the counter mode of operation, the counter can obviously be implemented by a linear feedback shift register with maximal period. So this is a counter. And then the filtering function is nothing else than a block cipher. So which means that the part of the internal state with corresponding to the key remains unchanged. Okay, so this is the case where the filtering function is very strong and the next state function is quite weak. But on the other extremity of this trade-off, we have the case where the next state function is very strong and the filtering function is very weak. This is the case, for instance, of the sponge construction, which is when it is used as XOF, because in that case, the absorption phase can be seen as the initialization process. Then we get an initial state, and we can generate a key stream by applying at each iteration permutation, like the Ketchak permutation, and at each iteration, we can extract some bits from the internal state. And again, this strong function, because we now need a strong function for us, the next state function, it can be implemented by a block cipher. And what we get in that case is what is called OFB mode. So you can see that, well, we have this trade-off and we have seen some situation where we have a very strong next state function and weak filtering function, or vice versa. But of course, we can have something in between. And what's the idea of having things in between? Well, this is an idea which was proposed, for instance, in LEX. So LEX was an e-stream candidate which has been proposed by Alex Biryukov and was broken 4 years after by Odd Dunkelman and Nathan Keller. But even if it was broken, I think that this LEX cipher is a very interesting design. So why is it a trade-off? Well, what is the idea? It's a bit like AS in OFB mode, but instead of waiting for the 10 rounds of AS for extracting one block of keystream, what we are doing is that we extract 4 bytes after each iteration of the round function. So the next state function corresponds to the AS round function. Of course, the key part is updated by the key schedule, by one round of the AS key schedule. And at each round, we extract 4 bytes of the AS inner state. And what happens is that since we extract 32 bits at each iteration, in total for the entire 10 rounds of the AS, we can extract 320 bits instead of 128 that we have for AES in contour mode or in OFBO mode. So we can get a higher throughput like that. So this is why I was saying that this kind of stream ciphers offer a more flexible design than block ciphers. But if we look at this design, then, well, there's an issue here. And the problem is that if we look at the key part of the internal state, then every 10th round, it is the same, right? So we can decimate the sequence and look at the key stream block obtained every 10th round. And then what happens is that we have such a design where the key part of the internal state is invariant. And then in that case, there exists some time memory data trade-off attacks which only take into account the X part of the inner states, so the part which is varying with time. And so this time memory data trade-off, I don't give the details, but it has a complexity which corresponds to the square root of the number of possible values for the X part of the internal state. So the lesson learned from this attack is that it's not a good idea if this key part of the internal state doesn't have a large period. So natural generalization of this type of design is instead of having instead of letting this key part invariant or changing it with a function which has a small period, then we can apply to this key part a function which is quite simple, like a linear function, but with a high period. And this leads to a design which is a construction which is followed by many modern ciphers. I think it was introduced for the first time in SNOW by Patrick Ekdahl and Thomas Johansson. And so it looks like this. So you can see it looks like the design we had in LEX. The only difference is that to what was the key part of the cipher that will be now denoted by Y. This Y part, it's like a key schedule, so it is updated independently from the X part by a simple function, typically a linear function, but this linear function, it has a large period. And the X part is a part which is updated by a more complex function, which is usually seen as a finite state machine and which basically corresponds to the round function we have in a block cipher. And so in this design, of course, at each time instance, we extract from the inner state, from the internal state, we extract a key stream block. And so, as I said, many modern designs use this kind of construction, but the respective sizes of the X part and the Y part of the internal state may vary depending on the stream ciphers we are considering. For instance, in grain, those two parts, they have the same size because the Y part is implemented by a linear feedback shift register and the X part is implemented by a non-linear feedback shift register, which depends on the Y part, but those two registers, they have the same length. For some other ciphers like SNOW2 or Zook, then the X part, so the part which is updated in a non-linear way, this X part, it's much smaller than the Y part, which makes sense because the next state function which is applied to the Y part is much simpler. But you can see that this unbalanced, it changed for the most recent version of SNOW because then as a Y part has a size which becomes closer to the size of the Y part, the X part has a size which becomes closer to the size of the Y part. Okay, so these are the designs that I'm gonna now study and analyze. And so I will say now a few words about attacks we can have on this kind of designs. So first of all, because this stream cipher, what I'm considering, as I said at the beginning, I will exclude related IV attacks. So what I'm considering are attacks on the key stream generator. And of course, there's a natural idea is to try to identify a distinguisher on the key stream sequence. So obviously, we choose the design and the filtering function in such a way that each individual keystream blocks which is generated is uniformly distributed. But the question is now, what happens if we consider several keystream blocks together? And so what we will study is what is denoted here by this capital F with some m here. This is the function which associates to an initial state x a segment of the keystream corresponding to m consecutive keystream blocks, right? And so this was called by Ross Anderson the augmented function of order m. And so this m is, of course, very important because the question is, when can we say that this augmented function of order m has a uniform distribution or not? So a first obvious remark is that when m is large, then the output size is much larger than the input size. So it's obvious that the augmenting function cannot be balanced. But it may appear that for even small values of m, then the function is not balanced. And so this is the case, for instance, of the counter mode of operation. The counter mode of operation, if we consider the augmented function of order 2, this means that the outputs of this function correspond to one ciphertext, the ciphertext corresponding to the plain text x, and another ciphertext corresponding to another plain text, which is different from the first one. Then in that case, it's clear that those two outputs cannot be the same because there are ciphertexts corresponding to different plain text. And so because of that, it's trivial that the augmented function of second order, it cannot be balanced. So what the question is, what is the minimum number m? There's a minimum number of consecutive keystream blocks that we have to consider together in order to find a non-uniformly distributed augmented function. But of course, well, we have to quantify what's the distance between the output distribution of this augmented function and the uniform distribution. And so to do this, what we do is that, well, we'll look at all possible values we can have for this keystream segment, z, and denote by this epsilon z here the probability that the output of our augmented function equals z minus the uniform distribution. And so the relevant quantity to measure how far the output distribution of the augmented function is from the uniform distribution, this is what is denoted by this delta. And delta, it has received different names. This delta, it is sometimes called the square imbalance of the function or of the distribution. It's also called the capacity of the distribution because it actually corresponds to the capacity of a transmission channel in terms of information theory. But well, this quantity, it is defined as basically the sum of all epsilon squared over all possible z here. And of course, this is multiplied by a factor which corresponds to the number of possible values for the output of the augmented function. And it appears that this square imbalance, it provides a very good approximation of the statistical distance between the output distribution of the augmented function and the uniform distribution. And because of this, it is well known that an optimal distinguisher for distinguishing this augmented function, it will require a number of samples, which is defined by the inverse of the square imbalance. There is, of course, a constant factor here, which is related to the success probability of the distinguisher. And so this works for any output alphabet. Of course, we are used to this framework because this is the thing that we are using, for instance, in linear cryptanalysis, but it is exactly the same for any output alphabet. So it is exactly the same in theory, But in practice, it is very different, because when the output alphabet becomes larger, and when the M, so the number of keystream blocks that we consider, it becomes larger, then it becomes very difficult to implement this distinguisher, because we have a lot of possible outputs. And also it becomes very difficult usually to determine or to find an estimate of the square imbalance of the distribution of the output distribution of our augmented function. So what we do instead is that we usually use simpler distinguishers, which are not optimal, but simpler to implement. And so it's quite easy to understand what we are using usually. When the alphabet is an abelian group, and so I'm going to suppose here from now on that the underlying alphabet of our stream cipher, this is the set of integers modulo q, where q can be any integer. So just think of q equal to 2, which is the usual binary case that we have. But well, from now on, I'm going to suppose that at each time instance, we produce a keystream block which corresponds to L different integer modulo Q. Okay, and if the underlying alphabet is ZQ, then it's nice because we can define a Fourier transform for our augmented function. It's defined like this, and this omega here, it's a complex number, which is a Q fruit of unity. And if you think of the binary case, this omega then is -1. And what you have here, this Fourier transform, it's the usual wash transform that we are using in linear cryptanalysis. But well, this works. You can define this Fourier transform for every value of Q. And what is nice with the Fourier transform is that it satisfies what is called Parseval relation or Plancherel relation. And in our case, this relation, it implies that the square imbalance of the output distribution of our function can be computed directly from the Fourier coefficient of the augmented function. It is the sum over all possible non-zero output mask of the squared moduli, because this is a complex number, of the square moduli of our Fourier coefficient with zero input mask. And so what is important, there's a factor, of course, which is not important, because what is important here is that if the output distribution of our augmented function is not uniform, this is equivalent to say that this square imbalance, this delta, is non-zero, then this is equivalent to say that at least one term in this sum is non-zero, because all terms in this sum are positive. And so what does it mean? This means that there exists at least one output mask, one value of B, for which this linear combination of the consecutive keystream blocks is not uniformly distributed. So this means that if the output distribution of the augmented function is non-uniform, then there exists a linear distinguisher for the output keystream segment. And of course, I say linear distinguisher, but the notion of linearity depends on the alphabet we are using. So here, this sum here, this is a sum over integer modulo Q. So this means that for a given cipher, we can see the cipher as a cipher defined over different alphabets. So for instance, if we consider a cipher whose output blocks are 32-bit strings, then we can define like this. We can see the cipher as a binary cipher, which means that in our case, Q is equal to 2. And then what we obtain like this, so this sum is a sum over F2. So what we obtain is a distinguisher corresponding to a binary sum of some keystream bits. But instead, we can also see the cipher as a cipher operating over Z 2 to the power 32. So Q is then 2 to the power 32. And this sum would be an addition modulo 2 to the power 32. And so like this, we get two very different distinguishers. So the second one is probably much more efficient than the first one, efficient in terms of it's more powerful, but it's probably much slower. And of course, they are very different. So as you can see, well, we have many different techniques for playing with distinguishers, and we also have some nice way to find distinguishers, for instance, with parity check relations and so on. So I won't detail this aspect, but instead, I will say a few words about correlation attacks. Because, well, usually as cryptanalysts, we need more than distinguisher. We would like to recover some part of the secret. And so remember that here the secret is the initial state of the generator. And there's something which is very tempting for a cryptanalyst, which is the fact that in our design, remember that the internal state is divided into two parts. And the Y part is a part which is updated independently from the X part. So it's very tempting to try to mount a divide and conquer attack on this type of designs, and this is called correlation attacks. So this is the cipher we're looking at, and so this Y part here, it is updated in a way which is independent from the X part, and so our aim will be to try to recover Y0, so the initial state for this Y part. And so there's a case where there's no hope to recover Y0 from the knowledge of a segment of M consecutive keystream bits. This is a case where any segment formed by M consecutive keystream bit does not contain any information on Y0. And this corresponds to the case where the augmented function, it is balanced, it is uniformly distributed for any fixed value of the Y input. In that case, this exactly means that a segment of M consecutive values of Z does not provide any information on the Y part of the internal state. And so the question is, well, what is the minimum value of M that we should consider to recover, so to be able to recover some information on the Y part of the internal state from an output keystream box? And this, again, depends on the cipher we are considering. So for instance, in Zook, then we can show that this it's possible to recover some information on the Y part of the cipher from two consecutive output blocks of the keystream, because we have such a biased linear relation. For Snow, it's not possible to, for Snow V, at least for Snow V, it's not possible to do this with two consecutive outputs of the keystream. We need 3 of them to recover some information on the Y part of the internal state. And for transistor, we need 4 output keystream blocks for doing this. And again, because of this relationship between optimal distinguishers and linear distinguishers, for the same reason, then if there's a way to recover some information on Y from M output keystream blocks, then there's a linear relation between those things, which means that which implies that we get such linear approximation. So now, once we have such a linear approximation, what could we do? Well, we are in a setting which is very close to a linear cryptanalysis. So what happens is that, well, we have such linear approximation. And so what we can do, and we don't need the next state function for the Y part of the internal state to be linear. In that case, there's an obvious technique which consists in performing an exhaustive search for all possible values of Y0, so the value we are looking for. So we just make an exhaustive search over Y0, and then for each Y0, we generate the successive values of YT. so the sequence of successive Y part of the internal state, and we compute the correlation between this sequence and the sequence which is derived from the key stream that we know. And then we choose the Y0, which maximizes the square imbalance of this sequence. So that's obvious, but this is quite expensive because the cost of this is the cost of an exhaustive search for this Y0, so the number of Y0s that we have, it's Q to the power, let's say Q to the power N, and we multiply it for each possible value of Y0. What we have is to compute the correlation of this sequence. So we multiply it by the length of the key stream that we need to consider. So the cost is this capital N, this length of this sequence, multiplied by the number of possible values we have for Y0. But what happens is that when this Y part of the internal state is updated in a linear way, then we can just rewrite this approximation like that, because then this part involving as a value of the Y part of the internal state at time t, it can be written as a linear function of Y0. And then in that case, it's possible to compute the square imbalances of all this distribution of all this sequence for all this Y0. We can compute all of them together by using a Fourier transform and then by using a fast Fourier transform algorithm. And so this means that because of this FFT, the complexity for computing all this distribution, the square imbalance of all this distribution, it's still, of course, the cost of an exhaustive search of on Y0, but it's not multiplied anymore by the length of the sequence that we consider, but instead it's multiplied by a much smaller factor. And so the fact that we can use a Fourier transform for this, it was first observed in the binary case by Schultz, Zhu, and Mitton, but we can generalize it to any alphabet. It's a bit more tricky when we are not in the binary case, but well, it still works. So this is the first way that we can use for making things faster and using the fact that the Y part of the internal state is updated in a linear way. And there's a second direction, which is that we can try to reduce the dimension of Y0, because we have this still this cost of an exhaustive search over Y0 appearing here. So we can try to reduce that term. And this can be done into two different ways. The first way, which consists in combining different linear approximation in order to have terms here which involve only fewer bits of Y0. So this means that this will reduce the dimension of the state on which we have to perform an exhaustive search. But the price to pay here, because we combine different approximation, is that we will decrease the bias. And another direction which is very nice and which has been observed by Yosuke Todo a few years ago is the fact that if we have a lot of linear approximation with the same beta, the same output mass, and the same bias, then we can use all of them, use the fact that we have many of them, and we can use this for reducing the dimension of Y0. So as you can see, there are very different techniques, and this kind of attacks, they have been studied a lot. And what is very nice is that this offers a general framework, exactly as what we have for linear cryptanalysis, and that this framework, it works for any alphabet, not only in the binary case, but for any kind of alphabets. And for instance, we can work with prime fields and do exactly the same kind of thing. And so, well, it sounds maybe a bit weird to try to design stream ciphers and to attack stream ciphers on a non-binary case. But, well, this is a situation which can appear when we look at a particular application, which is transciphering. So as I said at the beginning, transciphering, this is a solution to handle the huge cipher expansion that we have in fully homomorphic encryption. So how does it work? Well, I guess all of you know this. at least how fully homomorphic encryption works. So fully homomorphic encryption, that's a technique which enables to outsource some computation because we can evaluate the ciphertext corresponding to some f of x, where f is any function, by applying the homomorphic evaluation of the function f to the ciphertext of x. And then we will get the ciphertext corresponding to f of x. So we can evaluate some function by applying a homomorphic version of this function to ciphertext. The problem, so this is a very nice application, but as you all know, one of the problems of this fully homomorphic encryption schemes is that we have a huge ciphertext expansions. This means that for encrypting one bit, we usually need several hundreds of ciphertext bits, sometimes several thousands or tens of thousands of ciphertext bits. And so this, of course, poses a lot of problem in terms of communication and bandwidth. And so to handle this ciphertext expansion, what we are doing is that we are using a hybrid encryption scheme. So instead of transmitting the ciphertext corresponding to the encryption of the plain text of our data under the homomorphic encryption scheme, what we are doing is that we use a stream cipher. And so we transmit the ciphertext encrypted by a usual, symmetric cipher, but stream ciphers will be very good candidates for that. And so this is the ciphertext that we will transmit to the server. So there's no ciphertext expansion, that's a usual asymmetric encryption. And we transmit with this the encryption of the symmetric key, but encrypted by the fully homomorphic encryption scheme. So this is what we transmit to the server, but remember that the server needs to get the ciphertext corresponding to the plain text, but the ciphertext obtained under the fully homomorphic encryption scheme. And so to recover this value, what the cipher has to do is that it has to evaluate homomorphically the decryption function corresponding to our symmetric cipher. And so this means that we need to find a symmetric cipher for this transciphering, for which the cost of this operation, so which is the homomorphic evaluation of the decryption function, remains reasonable. And if you use like AES in counter mode, then the cost is much too high for applications. And so it appears that stream ciphers are very good candidates for doing this. And so, before going into the details of implementation metrics, I have to say that we can do this with two different settings. The first setting is the one I just presented, where we transmit the ciphertext and we transmit an encrypted version of the secret key of our stream cipher. But for a stream cipher, what we can do instead is that instead of transmitting the encrypted version of the secret key, we can also transmit the encrypted version of the initial state of the generator. And so this is the second setting, where the secret material now corresponds to the secret initial state of the generator. So what is very nice is that if we do so, then the server does not need to perform again the initialization phase. And so the cost of this initialization phase, it is not included anymore in the cost of the homomorphic evaluation of the decryption function. So it also means that in this kind of setting, we can choose an initialization phase which is quite strong, because its cost will be negligible. So this second setting, it's very nice. The only drawback is that it increases a little bit the cost, the transmission cost, because the initial state of the cipher is usually 3 or 4 times longer than the secret key. But so this is a problem if we are using very short messages, but this is not the case in the type of application that we are considering, because the data, the plain text corresponds to data on which we want to compute statistics. So this corresponds usually to long messages. So we will choose this second setting. And so this explains why initial state of the cipher, of the generator, is the secret which has been transmitted. And so now if we come back to the performance requirements, what is the cost metric? Well, what's the idea behind that? Well, this is that in a homomorphic encryption, we are working with noisy values. And each time we perform a homomorphic operation, then the variance of this noise increases. And if it becomes too high, then we have to reset the noise to the nominal level. And so this has to be done by an operation which is called bootstrapping. And this bootstrapping is by far the most expensive operation that we have in a homomorphic cipher. And so the point is that we must choose our stream cipher in such a way that we keep the noise growth acceptable through the operations. And so if we look at the kind of fully homomorphic encryption scheme that have been proposed like 10 years ago, like BGV, for instance, it's clear that the growth of this noise, it highly depends on the multiplicative depth of the cipher that we are using. And so this is why we have seen many proposals of different ciphers with different design ideas, which try to minimize the depth of the circuit implementing the cipher. And this is why we have all these proposals. But it appears that if we now look at more recent fully homomorphic encryption schemes like TFHE, well, the cost metrics becomes very different. So if we look at TFHE, for instance, the plain text alphabet, it is a set of integers modulo p, where p is quite small. It has a few bits only. And the main feature that we have in TFHE, which is very interesting, is that the bootstrapping is done at the gate level. What does it mean? It means that we have something called PBS, programmable bootstrapping, which takes as input an element in ZP and which resets its noise to a nominal level. But this programmable bootstrapping, it's also programmable, which means that it is also able to evaluate any function on this input. And well, the only constraint on the function, so this function is defined by its lookup table, so it can be a very complicated function operating over ZP. But if P is even, then it has an additional constraint, is that it must be negacyclic. So this is why I will focus on the case where P is odd, because I would like this programmable bootstrapping to be able to implement any possible nonlinear function. It will play the role of an S-box. And so what happens is that if we look at this PBS, then the time of this PBS as a performance, it highly increases with the value of P. So here you have the number of bits of P and the time of the PBS, and you can see that it remains reasonable only if P has 4 or 5 bits and not more. So this is what we will choose. And so this is for nonlinear operation and also linear operation in TFHE. It increases the variance of the noise. What happens is that if we compute a linear combination of some elements C and compute a linear operation like this, then the noise variance, it will be multiplied by a factor which corresponds to the square L2 norms of the coefficients alpha. So these alphas were public, there's no homomorphic evaluation of this alpha here. So each time we will perform a linear operation, we have to choose the coefficient of the linear combination in such a way that we will try to minimize this L2 norm. And so this is what we did in our our new proposal, and I will only say a few words on it. So this new stream cipher, which is well suited for this context of TFHE, it's named Transistor. So it has been designed by a group of people. You have the name, and you can see that there are people from symmetric crypto and people from fully homomorphic encryptions here. And so what are the design choices? As I said, we choose a setting where the initialization function is only done on the client side. And so it can be quite complicated. And we choose for that to generate the initial state by applying shake to the key and ivy. So this is why these related ivy attacks are not important. Then the plain text size, we choose, I said that this pin must have a 4 or at most 5 bits. We choose a prime number, the closest possible one to a power of 2, and we choose p equal to 17, which is nice because when we consider 15 digits in F17, then this more or less corresponds to 1 byte. And also, well, we will use linear feedback shift registers in our design, which sounds like it's a very bad idea because then each time we perform a linear operation, then the noise grows. So it seems that the noise accumulates in the register. But what we will do to avoid this situation is that at each time instant, we will recompute the linear function directly from the initial state, which means that there is no accumulation of the noise in the register. And so this is how this transistor looks like. As you can see, it follows the same kind of design as the one of Snow, Zook, and so on. So the general construction is the same. So the internal state is split into 3 parts. The X part is the part which is taken as input of the finite state machine, so as the round function we have for our ciphers. So this X part, so this function here, this FSM, it's like a round function of the A. This round function, we add this K part of the internal state, which acts as a round key. And so this round key, it is updated by a linear feedback shift register. So this is exactly the same thing as what we have seen before. And so at each iteration, what we do is that we extract 4 digits from the internal state X, from this X part, which consists of 16 digits, exactly as what we have in AS. And so the only difference is that we added here a Y part, a W part of the internal state. It's named W because it acts as a whitening element. So it is updated by linearly independently from the other parts of the internal state, and it is just added to the key stream block before outputting the value. So here you have the sizes of these 3 parts. The smaller one is, of course, the X part. And so what you need to know in more details is how this nonlinear next state function looks like. So as I said, it looks like the AS round function. So we have 16 elements in F17. And so what we do is that we first add the round key coming from the key part of the internal state, and then apply something which is the S-box layer implemented by PBS. And then we have a shift row, a mixed column layer. And the important thing is that we extract at each iteration 4 elements from this 16 element internal state, and these 4 elements are these positions here. And because these positions have been properly chosen, and because we are using an MDS mixed column operation, then it's really easy to prove that 3 consecutive output blocks generated by transistor, they are independent of the key schedule LFSR, so they do not contain any information on the key schedule LFSR, which means that we cannot apply a correlation attack on that. And this is by design. You can prove it with pen and paper. We don't need a milk for this. This comes from the MDS matrix and the positions where we choose to extract the 4 digits. And also we can go a bit further and see that the best fast correlation attacks that we could have, well, they will be based on linear approximation involving at least 4 blocks of the key stream, and we can give some bounds on the best square imbalance of this approximation, on the number of such square approximation, and so on. So there are, of course, more cryptanalysis work to be done on these transistors. So please, I would like to motivate you to do so. As I said at the very beginning, I think that we really need to have more cryptanalysis on stream ciphers. There are many open questions. Here are a few of them. So for instance, the question of algebraic attacks seems very different in the binary case and in the non-binary case. So while for correlation attacks, we have now, I think, a framework which applies to all cases. Also, we don't know how to handle different alphabets and different notions of nonlinearity, which is the case in Zook, for instance, where we have a binary approximation of the finite state machine applying to binary values, while VLFSR applies to elements defined in a prime field. So there are many open questions, but well, the main message of my talk would be, please look at this and try to find a nice theory and nice framework for cryptanalysis of stream cipher, exactly as what we have for block ciphers. And I need to end by thanking my co-author of Transistor. I would like also to say a special thanks to Willy Meyer and Thomas Johansson, who are sitting in this room and know much more about stream cipher than I do. And of course, a special thanks to those 2 cryptographers with color pictures that gave me these initial questions. Thank you.
Thank you, Anne, for the nice talk. I think it's time for one short question. Yes, please.
So what is, when we start cryptanalyzing, what is would be the weakness if you don't add the W part?
So, well, what you say is important is that, well, all security evaluation that we did is without the W part. So I think we have to start from to define the quantity of information we can find from in the keystream block. So we know that we have to consider at least 4 blocks of keystream together, and then we could try to combine these output blocks in a nonlinear way to get better distinguishers. This is possible, but it's quite difficult to do in practice. But well, I don't know if we can move to more optimal distinguishers. The question of algebraic attack for me is quite unclear. Well, well, the attack we can think of like writing an algebra and solving an algebraic system, then you can evaluate what happens. But if we can find clever model for that in the same sense that we have the attacks defined by Willy and Nicolas Courtois some years ago, this I don't know if we could find a non-binary version of this kind of attack. So
I think due to coffee break, I would like to ask you to ask Anne follow-up questions in person. And please thank Anne again.